It's my absolute pleasure to welcome everyone to this to the MERL Spring Seminar Series, and to welcome our speaker today, Sebastian Gros, who will present his work on the integration of reinforcement learning and model predictive control. I'm going to say a few things, just backgrounds as background information. So Sebastian did his PhD at EPFL in Switzerland, after which he became a postdoc in the optimization-based controls group of Professor Moritz Seal at TU Leuven in Belgium. And it's there actually that Sebastian and I met in 2012, when I was still a master's student, and I was actually very lucky to work directly with him for multiple years during my PhD research. And so after this postdoc, Sebastian became an assistant and associate professor at Chalmers in Sweden, where he had strong collaborations with Volvo and autonomous driving and smart traffic. And since 2019, he is currently a full professor at NTNU in Norway and head of the Department of Engineering Cybernetics. And Sebastian is doing a lot of research on theory and algorithms for optimal control, with currently a focus on safe reinforcement learning and data-driven MPC. And he works on different applications, including mobile robotics, autonomous vehicles, and smart buildings. So I think we're all very excited for your talk, Sebastian. So the floor is all yours.
Cool. Thanks for having me. Thanks for the introduction. Okay, let me try to share the screen then. Let's try that. I guess you see that now.
Yes.
All right. Let's do this. All right. Yeah. Okay. So that's gonna be my talk. So I give a catchy title, but I hope you all noticed the question mark in the end. I'm not gonna try to sell you carpets or something like this. I will try to give you a pretty clear view of what we are doing and where I think it's useful, and where maybe that's not the best way to go. So, but all is about combining reinforcement learning and MPC, as Reen said. Just a few forwards before starting. I should present my department since I'm heading it. So that's the Department of Engineering Cybernetics. I don't think there are many departments named that way in the world, so that's a bit of a fancy name for departments. That's NTNU Norway. It's the biggest university in Norway. And the entire department is focusing on cybernetics activity. So that's mostly mobile robotics, air, land, and sea. We have some large research centers about that. But we also have different programs. We have a new focus on small satellites with the first launch of a homemade platform in 2022. And we also have some activities on smart grids, smart houses, and also this thing here, that's a group building artificial pancreas, for example. So we have quite a collection of different things. I cannot talk about everything here. Concerning the talk itself, so that will be a lot more specific than that. The context of this talk is we see a lot of research on combining learning and MPC in lots of different ways, or learning and optimal control. And what I want to explain here is our take on this topic. And I think we have a slightly different view than most groups on the way that can be approached. So I'm going to summarize some years of research in this slide. So I'll stay a little bit on the surface, but I want to give you the main concepts that are underlying what we're doing. Yeah? But it will remain a bit conceptual. I've tried to minimize the amount of math, but of course there is still quite a lot of that. I'm pretty sure that you guys can take it. And I'll focus on the main ideas rather than detailing the results. So I hope that will work for you. Okay, so if I try to paint the landscape a little bit of what we are trying to do, I think the best place to start with is to talk about Markov decision processes, MDPs, because that's a little bit the mathematical workhorse that we use when we talk about optimal control, and that's the framework we should use when we talk about MPC and optimization of dynamic systems. So in that context, probably most of you know about this, but I'll recall that a little bit anyway. So we have, I'll try to push this a bit aside. Not really here, maybe. Yeah, I'll move it a bit to free the slides. So we have a classic view on dynamic systems, this discrete state and action. Some would call it input, but action is quite common. And going to a next state. And this transition from state action to next state is assumed stochastic typically. And associated to that, we have a cost function, typically a function of state and action, sometimes also S plus. But that's the way of measuring performance instantaneously. So at a given time instant, this tells you how well you're doing at that specific time instance. And on top of that, you would work with policies. So that's telling you how for a given state you will act on the system. So A equals pi of S. And then you have a performance index, sometimes called J, function of that policy. And this thing here is essentially saying I'm gonna sum all these cost functions to infinity on the state and actions that will be visited by my system. I'm gonna discount it. So this gamma is something typically less than 1 power k. So that's a factor that will decay for the longer we look into the future. Then, because everything is stochastic, I will take the expected value of that. So visualizing a little bit can be easier. So you have to imagine that you start from a possible state here, and then the future is uncertain, you're stochastic. You need to take a decision at this time instant based on the state you are in. And then as time proceeds, you will actually land on a new state. Now it becomes deterministic, but the future remains stochastic. So at every time instant, you need to take a new decision. And you solve an MDP when you build an optimal policy. So you minimize this J. Some would maximize it, but that's the same story over the policy. And for this funny one state, one input system, here is the optimal policy actually for that system. Okay, so if you did not know about MDPs, probably you did, that's the way it works. And MDP, that's a very useful mathematical framework to discuss optimal control. It basically contains most of the questions you may want to discuss in that context. And solving an MDP is a little bit the holy grail of optimal control. If you can build this policy, you're basically good to go in every sense of the term. Yeah. So that's a fairly generic way of discussing optimal control. Okay, now the second part of or the tool that we will discuss in this talk, that's MPC, so a Model Predictive Control. Same here. I know that a number of you know about MPC, but in case you don't, I'll make a quick reminder of how that works. So essentially, you can summarize it in one line. You optimize a plan over a finite horizon, and then you extract the first action you wanted to take on your system, and then you repeat at the next time instant. So if we try to describe that a bit visually, you can look at this graph here on the right. You would have the state on the lower graph, the actions on the upper graph, and you are, say, in a current state here. That's your current time, this line. And you make a plan from that state of the future of your system. So that takes a model to do that. You make a plan of the actions you want to take on that system, and then you will apply on the real system the very first control move you find in that plan. And then when you land on the next state, you will redo the whole procedure. So you rebuild an entire plan, always on a given window that kind of lies with you forward. And of course, your state or your system may not land exactly where you thought you would, because your model may not be exact. So you may have this picture where your predicted trajectories are a little bit less obvious than what your model thought. So mathematically, you can write an MPC. Here I missed or I omitted a few ingredients. You'll probably see that if you know a lot about MPC. But roughly speaking, you optimize this L function over a finite horizon, this n-1 typically. This is the model that describes how the system will react to a sequence of action. And I will note U and X for my state and actions in the future, as opposed to S for my current state, and A for the action I apply to the system. So you'll start your system at the initial condition S, that's your current state. You optimize this thing that gives you this action plan and the associated trajectories you think your system will follow. So the MPC is it's based on planning on the future, by repeating this planning all the time for the later states, you actually build a policy. So you can call it Pi MPC, and that's the very first action in your sequence, the U0 star, if you want. So MPC is used quite a lot, and nowadays more and more in the industry. It's a powerful tool to control constraint systems, because I don't show that here, but you can introduce constraints in the story. So now you can imagine they are in the cost. But it's also increasingly used as a way of, or practical way of doing optimal control. So trying to get an optimal policy pi star and optimize the performance of a system. And I'm saying that maybe you already know where I'm going with that. MPC has been used a lot for steering the system to a reference point, like reference somewhere, reference speed or whatever. In which case your cost function is indicative of trying to get to that specific point. But nowadays we discuss more and more using MPC for driving the performance of the system. So it's not necessarily driving the system to a specific state, but just extracting performance of the system. And I'm specifying that here because that will come back later in the slides. Okay, so how do we do MPC? It's fairly basic in the end. If you have a given system, so you develop your MPC scheme and that builds a policy, Pi MPC, and now I'm gonna have theta that pops up here because the MPC is based on a model and the model has some parameters and we need to decide what these parameters are. So the policy you get from your MPC scheme will depend on the parameters that are inside your model. And how do you get these parameters? Well, you can guess them, you can have a knowledge-based understanding of these parameters, and you can try to fit your model to the data you have on your system. So you may have collected trajectories on your system. Try to fit your model parameters or fit your model to the trajectories via adjusting the parameters. Then inject that in your MPC scheme. It's a very, very classic way of doing MPC. Now the question is, if you do that, does it work? Well, it may. But not necessarily, because there's no guarantee if your model cannot capture the real system dynamics. Maybe they are stochastic, for example, they usually are. There's no guarantee that this process will do anything good. Actually, you can build examples where doing this sysid and injecting the parameters, that can even degrade the performance of your MPC scheme compared to, say, keeping a reasonable guess for theta. That's not exactly a new thing. This issue has been well known in the context of database process optimization for about 20 years, I think. And before that, it was also known in adaptive control, actually, that this whole schematic is not necessarily working. Yet, this is pretty much what a lot of people try to do with learning an MPC nowadays. They basically do sysid-like solutions. So now we changed a little bit how we think of sysid with all the ML machine learning tools in the background, but it's still kind of the same concept. So now instead of doing basic sysid, we talk about Gaussian processes, reproducing kernel Hilbert spaces, Bayesian neural network, and so on and so forth. So you build that and then you inject that in your MPC scheme, and then you hope for the best. And I really don't want to dismiss these things. I think it's a very good attempt at bringing machine learning into MPC, but I don't think it's a complete story. So in this talk, I would like to give another side of this story, which I think can be useful. So what is the problem with that beyond what I discussed just before? Because in the end, maybe if your machine learning tools are powerful enough, they can capture the system dynamics fairly well. And then maybe you bridge the gap to having a very solid and good MPC scheme. Well, there's still some problems because if you really want to capture your system dynamics, you'll probably end up with very complex models. Imagine a very big neural network or something like this, which will turn into complex optimization. So it's not clear that when you have done all this work to get a really good prediction of your system trajectories, this will result in an MPC scheme that you can solve online. So you may have limitations in the model structure that you're using anyway. And then what is the best theta that you can select in that modeling structure? If you select that theta from trying to have the model imitating the real system, there's no result anywhere that tells you that this theta that best fits the trajectories of the system will also be the one that yields the best policies in the MPC scheme. It's actually deceivingly simple to build examples where it actually does not work. Like the theta that best fits the real data in terms of prediction may actually not do a very good job as a model for MPC. So I'm going to make a bold statement here, but the idea of reaching the optimal policy by doing machine learning over the data and inject that in the MPC scheme, hoping that this will give you the optimal policy, that's a little bit wishful thinking. It may work, but it's not, there's no guarantee. All right, I want to elaborate a tiny bit more on that to explain a little bit some important things in my opinion. So at the end of the day, what we are really asking here is if MPC can solve MDP. So MDP is it's about getting the optimal policy for a system, knowing that the system is potentially stochastic and so on and so forth. And you have your MPC scheme on the side that's based on a model. In principle, the model could be stochastic as well. You could try to capture this distribution uncertainty in your trajectories, but still that model may not be perfect. Okay. So can MPC solve MDPs? Well, it can if, of course. So there are a few things that you need to change in here to bridge the gap between your MPC as a policy generator to your MDP. One is, of course, well, MDP wants an infinite horizon, so you should have that in your MPC scheme. It should also be discounted. Okay, we can discount the MPC scheme. But, of course, the last problem is you need an exact model. If you have all these ingredients, yes, of course, your MPC will give you the optimal policy. We can live with discounting. It's actually not such a big issue. And infinite horizon, of course, we cannot do that, but we can get very close to that. Just use a long enough horizon, terminal costs, all these ingredients. In principle, you could make an MPC scheme that behaves like the infinite horizon one. But of course, the big problem is this one. An exact model is not going to happen. And again here, if your model is not exact, of course, your pi MPC, the MPC policy, may be close to the optimal policy, pi star. But there's no easy relationship between how much model error you have and how much performance you lose. That relationship is very complex. And that, in my view, is bad news for using ML-based modeling inside MPC. Again, not to say that it's not useful, but it will probably not necessarily bring you to pi star. All right, so another object in the talk is reinforcement learning. So here again, I know that a number of people work with reinforcement learning, so I have nothing to teach to them. But just in case you're not fully on board with what it is and how it's placed in that context, I want to talk about this here very briefly. All right, so this optimal policy pi star is, or can be at least, an extremely complex object. So here I just show one, and that's for a very, very simple system, and it already takes this weird shape with this curve here that is obviously nonlinear, and then you have non-smoothness here in some points. So even for a very simple example, you already get something fairly weird. And if you go up in dimensions in the system, like larger states, larger action spaces, that just explodes into something extremely complex. So of course you cannot calculate pi star on most problems. So what we do typically is replace pi star by an approximation. Let's call it pi theta. Now the theta would be parameters inside the policy. And then what RL does is to try to tune these thetas from the data, typically not relying on a model, or not directly at least. Then what do you use for pi theta? In principle, you could use any rich function approximation, but what you want is something that works well in high dimensions. If you have a large amount of information that comes into the policy. You can think of images or stuff like that. So then you want function approximation that works well in high dimensions, and in that context, deep neural networks perform well. So that's a strong motivation for using that in reinforcement learning. And then on top of that, I'm summarizing brutally here an entire field of research, but roughly speaking, you try in reinforcement learning to tune the thetas such that you minimize this J function that we discussed before. RL people usually maximize, but that's no difference, of course. So you try to do this thing here, this minimization from real data, typically. Again, that's a bit of a shortcut. There are different methods in reinforcement learning that do different things, but roughly speaking, that's the goal. All right, I don't mean anything bad with this picture, but for control engineers, reinforcement learning looks a little bit like this because we don't really understand how you set up these deep neural networks and how you decide of the structure, the number of neurons, and so on and so forth. So it feels a little bit like witchcraft. Again, nothing dismissive here. It's just that we like to have very clear procedures to get to a goal, and if we need to tweak around, we tend to be uncomfortable. But more seriously, when the policy is based on deep neural networks, of course, it's not so easy to get the correct structure in your neural network. It's not so easy to initialize it in a good way unless you already know kind of where your policy is supposed to be. It's not necessarily easier to treat constraints in a problem implicitly, unless there are just constraints on the actions. But if it's on the state space, that's more difficult. And if you want to start certifying things, you would typically want to go to simulation-based certificates. So build a model of the system, simulate a lot, and check what's happening with your policy. So that can be a problem for some applications where this is possibly considered as not good enough. All right, so that was a bit of background stuff. Now I want to shift to a central result on learning and MPC, which I've been presenting this result for a few years, and I usually get some surprise reaction in the room still nowadays, so I think it's still worth talking about it. And for me, it's a little bit of it gives a bit of hope in the learning and MPC, this result. So I'll try to explain that. But I need to take a bit of a sidetrack towards value functions. So if you're not into optimal control, that will be a bit technical possibly. If you are into MDPs and RL, that will be your obvious daily life. But let's try this. So we have our MDPs on one side. The goal is to find the optimal policy, pi star. And I have my MPC on the right, the usual stuff, discounted, stage costs, finite horizon model, and so on and so forth. And this MPC gives me a policy. So the value functions, there are things that are underlying an MDP, and they are a bit abstract objects. So you have the V star and the Q star. The V star is essentially the same thing as this thing we try to minimize, but that's for a given action. So, a given state. So if you're in a given state, this green S, you start from here and you run your optimal policy. What is the expected cost you'll get? And if you change state, you may change this number. You may be in good states, bad states. And the Q star is almost the same, but now you don't specify only the initial state, but also the first action you take, and then you follow the policy. All right, so these two objects, very fundamental in reinforcement learning. Actually, a large number of methods are trying to approximate the Q star. Q learning, that's one type of method. Because if you get the Q star, you get the optimal policy as a byproduct. So it's very powerful if you can do that. Okay, so why am I talking about this? Why? Because the MPC, on top of giving us a policy by MPC, it also gives us value functions, or V and Q functions. The V function is quite obvious. It's the optimal cost you get from your MPC. It is actually a model for the V star of your problem. If your model was exact, the horizon was infinite, and so on and so forth, this V you get out of the MPC would be the V star. What about the Q? Well, that's the same story, but you just impose on top of that the first control move, the U0, is selected. That's this blue A. So the MPC also gives you a model of the Q function. If the MPC scheme was perfect, QMPC would be Q star. All right. And remember, if you can somehow capture these value functions correctly, you also have the correct policy. So it's very powerful to know that, or to conceptualize that the MPC scheme is carrying these objects. Yeah, that's some details. So these fundamental relationships between Q and V and pi are satisfied by the MPC scheme. But again, because the model will probably not be very accurate, the same as pi MPC is hopefully close to pi star, this value function or this model of the value functions are all hopefully close to the V star Q star, but they'll probably not be exact. And the only way you can get to being exact would be to have an exact model. So that's not going to happen. All right, so here is the central results. So I'm going back to my MDP, my MPC, my value functions. And again, in general, it's not going to happen that your MPC gives you the exact pi star, V star, Q star. But if you start to tweak with your cost functions, so that's a terminal cost, that's a stage cost. I added this ingredient just to be a bit technically correct. So if you tweak these cost functions under some assumptions which are not extremely restrictive, you can actually match the policy and the value function with your MPC schemes. So in short, that means your MPC scheme, even if your MPC model is not perfectly accurate, your MPC scheme can capture your optimal policy and value functions. If you have constraints in your MPC scheme, they may also need to be modified the same way. And this result is actually valid for all kinds of MPC scheme. If you do classic, robust, stochastic, economic, all these things, they all fall under the same umbrella. So what does it really mean? If you're curious about this result, there is a paper in TAC 3 years ago that explains that in detail. It's quite technical, but hopefully it's readable. Okay, but what is the bottom line with this? If we go back to learning an MPC, it's meaningful to adjust the model possibly, but adjusting the cost of the MPC scheme is very meaningful as well, and adjusting the constraints. And if you read papers on learning an MPC, you see people doing that. Actually, they tweak the cost as well, but they don't explain why. So, well, if you are doing that, here's why. There's a very good reason to do that. And that's a very interesting result, in my opinion, because now it tells you that actually, in principle, you can solve an MDP with your MPC scheme, even if you give up on getting a perfect model. All right, so what does it mean in practice? And that's where MPC and RL meet. Because RL, again, is trying to minimize this J function, the performance index. Typically it does it, or at least one part of the RL methods do it via trying to estimating the gradient of this function with respect to theta, and then take gradient steps along that. So that's policy gradient methods. And on that side, on the right side, you have your MPC scheme. If you modify your cost, not just the model, you can recover everything correctly, like the optimal policy and value functions. So the problem, of course, is that this modified costs, if you had to calculate them, you would basically solve Bellman equations or something along this line. So it's very complex, and you would need to know the system dynamics anyway. So it's completely useless unless you put yourself in a learning context. In that context, your costs, they become parameterized functions, and then you could use reinforcement learning or any policy improving tool to try to tweak these cost functions. So this L theta, T theta, they become things you learn from the closed loop trajectories. Now, tuning the model, there's nothing wrong with that. In theory, you don't need to do it, but of course you have assumptions for that to work. So tuning the model is also very meaningful. And I'll come back to this in a bit. And you can think of it as giving additional degrees of freedom inside your MPC scheme. And yeah, so reinforcement learning is an obvious toolbox to tweak your MPC parameters, so model and cost functions. All right, so if we dig a little bit further on this basic result, so it's useful to modify the cost function, and we know why, and the MPC scheme can in principle give you the optimal policy without an exact model. So if we go back to, oh yeah, there's a question.
So T theta is basically a value function. So is your theorem basically saying that if you know the value function, you can approximate the Q function arbitrarily well given a large n?
The T tilde would actually be a modified value function. So it's not even V star, it takes some modifications if your model is not exact. On the L
that's
tilde,
T tilde. But without the tilde, T is the value function.
The T, yeah. Yeah. So the T ideally would be the V star if your model was exact.
Yeah.
So if you could plug the V star in here, you would have built an infinite horizon MPC. In practice, you cannot calculate V star, so you replace it via an approximation. And on top of that, now the model is not exact. So even if you had V star, it would probably not be the right thing to have.
So is the argument a bounded deviation kind of argument?
Say it again.
Is this ultimately a bounded deviation argument? If you
maybe I'm not very familiar with this type of arguments, but so if you're thinking about the T tilde, L tilde, what happens here is it's a telescopic sum construction. So if you modify each stage cost in the right way, you have things canceling out despite the model being not exact, and you recover your Q star essentially. That's what's happening here.
Right. Yeah. Okay. Yeah. So you need to bound the deviation in that sum.
Exactly.
The deviations that cancel out.
Exactly. You need the cancellation to not be infinity minus infinity. Otherwise, things don't make sense. That's why you have the assumptions coming in. Yeah.
Understood. Thank you.
Okay. All right. We were here and a bit further. Let's go for, yes, here we go. All right. So now I want to dig a bit further into this and discuss a bit more in practice what happens with these things. And now I'm gonna also introduce some constraints just to be a bit more complete. When they are not here, you can imagine that they are in the cost. Why not? You can just make it costly enough to validate the constraints, and then you're good to go. So this combination of RL and MPC, that's about using RL tools to tune your MPC parameters. And I can think of two ways of looking at this idea, because you can look at it from the RL point of view or from the MPC point of view. So if you look at it from the RL point of view, what you would want to think is that this MPC scheme now is a structured function approximator. So normally you would use deep neural networks typically to do that. Now you use an MPC scheme to approximate pi QV in one shot. So it's a structured function approximator. It contains prior knowledge through the model. So it's easy to embed that prior knowledge if you have it. You have an explicit way of handling constraints because you just write them down in the MPC scheme. You have an easy way of using predictive information. I'm going to talk about smart house if I have time in a bit. So that's where you have a lot of predictive information, for example. And another interesting aspect of it is that you do get some explainability of your policy through that, because there is a plan behind your policy. You can say, well, it wants to do this because it wants to bring the system there, for example. So that's one way of looking at this approach. If you come from the MPC side, the way you may want to look at this is that you basically use RL to improve the closed loop performance of your MPC scheme. And you do that by you stop or you give up on the perfect model, and instead you try to adapt the whole MPC scheme to get your optimal policy. And the theory tells you that you're doing something right. And quite important, I think, because it's not obvious always, if you use RL on your MPC scheme, you will not get model fitting. You will get something else, and you will see that sometimes RL is actually detuning the MPC model from fitting the trajectories in order to gain performance. It's very easy to build examples where that happens. All right. Okay, so now we can use these concepts and go around and start grabbing results. So I'll just mention a few of them here. Again, more at the conceptual level. One aspect is stability by design. So what do we mean by stability here? Maybe obvious, maybe not. But the question is, if you close the loop on your system with your policy, will your trajectories converge to some steady state value, or will it just keep oscillating around and going around or going to infinity? Now, that's in the absence of disturbance, of course. So that's the question of stability. It's very central for control engineers, stability. And if you build an optimal policy for a given system and a given L function, like this stage cost that we try to minimize, there's no reason this pi star would be stable. It may decide to explode your system or make it unstable. And when you build or you try to build pi star from, say, a deep neural network, the stability of that policy can be difficult to verify. You probably want to simulate a lot unless you have a very specific case. So why do we care about stability? Well, maybe we don't. And it's not always the case that we care about that, but for some application it may be important. Some examples will be if you are optimizing a plant, it may not necessarily make sense that the policy would want to destabilize the plant. There are some cases where it does, but usually not. If you think of a self-driving car, you probably want to drive at a steady speed, for example, in a steady scenario. Why would the car want to change speed all the time? So this question of closed loop stability, it's a bit of a health check on your policy in some sense in a number of applications. All right. So when you use MPC, then you suddenly inherit a lot of results on stability. And there's a very mature stability theory behind MPC, about 20 years of publications. So you're well equipped to discuss it. And I would say it's an ongoing story. There's even results appearing soon on these questions of stability in discounted cases, stochastic cases, and so on and so forth. There are still gaps to fill, which are being filled recently. And actually, I should say it's not entirely clear yet on how to leverage on these very recent results. So that's something that the future will tell. But the whole theory that we have in MPC, it is a little bit verification oriented. So given a problem, I will try to tell you if that problem will give me a stable pi star or not. When we move to the learning context, we have an opportunity to flip this verification-oriented view to a design-oriented view. So how can I build an MPC scheme that is stable by design and through learning converge to something like the optimal policy? And again, very high-level view of this. But roughly speaking, if your policy is coming from an MPC scheme, you can describe a set in the parameter space of your MPC scheme for which the MPC scheme will be closed loop stable. So you have this theta stable set. And then, so you know that as long as theta stays in that set, you'll be good in terms of stability. And then what RL does on top of that is give you or propose steps in the parameters that will improve the performance. So they will typically look like this if you do policy gradient, for example. And then it becomes a fairly simple game of using this theta stable set to contain the RL updates inside the stable region for the MPC scheme. Yeah? So you can convert this simple gradient step into a QP-like step where you try to follow delta theta if you can, but you ask that the updates remain inside the stable set. So then what happens here is that if your theta star is stabilizing by construction, because the problem is in this way, then your pi theta will converge within the limitation of your parameterization to pi star. And that's a very nice observation. If pi star is not stable, because the problem made it unstable, then your pi theta will converge to the best stabilizing policy, so the stabilizing policy that has the best performance. Another question.
I think Matt still has his hand raised from before. I don't think
Okay,
there's
it
any
was not.
question.
Okay.
My apologies, but while my name's been called, so theta, it's very difficult to know for certain classes of approximators like DNNs what the stable set would be.
Yeah.
Is there a particular class of function approximators where that can be calculated in advance?
I did not hear very well, to be honest.
Sorry, is there a set of function approximators for which you can characterize the stable set of parameterizations?
In the MPC context, yes, with some caveats. We are not completely there yet, to be honest. But when you set up your policy from an MPC scheme, there are some.
And it's a polytope.
Say it again.
Sure, that it's a polytope for simple linear MPCs.
Yeah, it depends a little bit on how you parameterize the scheme, but yeah. It depends a little bit. It can be an SDP in some cases. It can be a QP type description with a polytope in the theta stable, but it depends a little bit on how you set up certain things.
Right, but for non-trivial approximators like a DNN, we're nowhere near being able to characterize these stable sets, right?
Yeah, I mean, but if the policy is really coming from a DNN, I don't know how to describe the stable set for that. I think it's not easy at all. Yeah.
Okay.
Just close that. Yes. Okay. Yeah. So I was there with my QP type stability constraint RLMPC. We have questions about that because when you talk about stability in the context of stochastic systems, things are much less straightforward as deterministic ones. So there is a theory for the stability of optimal policies inside MDPs, but it's not so easy to leverage that theory yet. So we are looking at it and how to use it in practice. If you're curious about the results, they are actually not yet published. They are almost there. So you can ask me if you want to know more about that. Very similar question, the question of safety by design. It's a very similar slide and it's very similar arguments. So what do I mean by safety? That will be that the closed loop trajectories of the system stay in some safe set S, which I know that's states that I consider safe. With probability 1 under my policy pi theta. So what is this S? That could be, well, the car is on the road or the plant is operating safely, whatever you defined as safe. So I'm just assuming you know this set S. What is hard is to predict that the trajectories will remain in that set in the future. If you look at this example I showed before, you can imagine that this set S is this interval between these two lines. And here actually you see a little bit of violation down here. So you can make your pi star safe if in the MDP you put an infinite penalty on leaving the set S. Mathematically, that's very easy. In practice, it's much harder. If you want to do learning from that, that's gonna be tricky. Of course, you can replace infinite by a large number and so on and so forth, but there's a number of practicalities that make it not so easy. In any case, when you develop a policy from a deep neural network, I think it's not very easy to verify safety or prove safety outside of very large simulation campaigns. So a little bit the same questions as stability. But there comes in a specific tool in MPC, that's robust MPC, which is taking the whole thing story one step further and is basically trying to model how big the dispersion from the model can become inside your system trajectories, or basically trying to build a model of the spread of your trajectory. So this illustration here, that will be if you start from this state here, and that will be your set, this ball, and you try to contain your future trajectories inside some sets, often polytopes or ellipsoid or something fairly easy to describe. So it's a worst case view on the problem. Robust MPC is not always very easy to manipulate, but it is a tool that exists and that works, at least in the not too complex cases. So if you build a policy from robust MPC, then it's pretty much the same story as before. You can describe a set of parameters for which the system will be safe, and then the learning aspect becomes one where you try to follow the recommendations of RL. RL targets performance, but you contain these recommendations in your safe set. So you land on the same formulation as before. I guess you obviously see that you could combine these two things together, theta safe intersection theta stable, and you could build a learning scheme that is safe and stable by construction or constraint to be that way. And same as before, if pi star is safe, then for if your parameterization is rich enough, your pi theta would converge to pi star if everything goes well. And if it's not, if pi star is not a safe policy, then your pi theta will be the most performant safe policy for your system. Current questions: if you use linear MPC, so if you accept to use linear models inside your MPC scheme, it's fairly easy. We have very good tools for treating that. If you want to use nonlinear models in your MPC, then it becomes a bit trickier. We may get around this one day with very high computational power, maybe, but the math are a little bit blocking this direction. Right. I heard that some of you are using safety filters in RL. It's fairly strongly connected to this question. Now, if you design a safety filter, you're basically trying to predict what actions you can take on your system that will leave it inside the safe set. And if you do that, you may want to be aware that you need a little bit of precautions in how you do the learning if you are constraining your policy inside some sets. All right, another interesting view on this, because now I've been building up this story where in some sense the model can be inaccurate. Well, there are some assumptions on which indirectly tell us how inaccurate it can be, but that's not very clear what's happening behind this. So what is the role of the model in this story? Well, the previous slide is one answer to that. So the model should be able to capture how bad things can get in terms of the constraints. So the model can be a safety tool in that sense. But that's not the whole thing. Sorry, I'm talking about the next slide. Let's come back to this one. Yes, if you have an observer in the loop, that was the story here. Because so far I've just talked about the MPC. Most often you have an observer in the loop. So some block here that will take the measurements you get from your system and give you a state estimation S hat. So you may not measure the full system state. So it can be Kalman filter, EKF, MHE, particle filter, whatever is best for you. So what happens if you do that? In my view, you should consider the observer as part of your policy. Why? Because this observer is also going to be imperfect. It may also be parameterized, for example, if it contains a model of your system. And if you think about it, your policy is pi MPC, function of the S hat, which is itself a function of the measurement through your observer. So your learning should apply to this pi theta, not just the pi MPC. Beyond that, the math just becomes a story of chain rules. So for example, if you want to calculate the gradient of your policy, that's often used in policy gradient methods, you basically differentiate throughout your setup. Yeah, just an example of simulation here. That's before learning, the first part, that's the cost you get. Then you start learning on the MPC, you see a clear drop in the cost, so you improve the MPC scheme. And then you also extend the learning to the MHE and you see a further drop in the performance. So just an example where that shows that there is a clear benefit in learning not just the MPC, but also the observer together with the MPC. And what we've seen in simulations and examples is that this thing is especially useful if you are actually missing some states in the MPC model. So you have the true system may have a pretty large state space, and you boil this down into a smaller system with an observer on top of that. It's helpful to have a tuning of both the MPC and observer together. Yes, that's I started pitching that slide. Yes, so I kind of threw the model off the window with this story, bar the assumptions. And the question is, should we forget about this this model, and should we forget about fitting that model to the real dynamics? Because the theory says that we could, in principle, give up on fitting the model on the system trajectories, just follow reinforcement learning for tuning the parameter. And the answer is yes, fitting the model is still meaningful. There are two aspects to this. Safe learning, the way I described it before, your model is supposed to cover the real system trajectories. So if you remember this picture with a circle, you want to model how your system will disperse. And then you're doing a specific form of SysID, that's called set membership. Try to enclose the trajectories into something. But the second aspect is explainability again. If your model is not fitting the real system very much, then your policy could be optimum in principle if you change the costs, but it becomes hard to make sense of the plans that your MPC are providing. If your model is kind of fitting the real system or kind of representing it in, say, expected values or something like this, then it becomes a lot easier to give explanations as to why the MPC is taking some actions. So still very meaningful, but how do you combine system modification and reinforcement learning? There are two different things. They can even they can try to do different things or pull in different directions. So how do you make them cohabit without conflicts? And we looked at this a little bit, and there are some solid answers in my opinion. One thing we know is that reinforcement learning should supersede SysID, because optimality is more important than fitting, at least if you're going for performance. You can implement that in some ways for Q-learning quite easily. For policy gradient, it's we understand how to do it, but it's a bit more technical. A few more ideas in a nutshell. I mentioned safety filter. We published something on how to do it correctly with RL. Otherwise, you can create some bias in your learning. We have discussed safe explorations in some contexts. MPC can help with that because you have your constraints in the scheme. We've discussed how to do mixed integer MPC and RL. There are a few subtleties here in some contexts. We've discussed how to optimize the meta parameters of the MPC by RL. So I'm thinking about horizon length and state-dependent horizon length triggering the MPC on some events and so on and so forth. We also discussed how to do MPC and RL on strongly economic problems. That's typically problems where you start having bang-bang policies or very aggressive policies that go max-max, for example. In that context, you need to be a bit careful when you do reinforcement learning. And an example of something we're doing at the moment is to try to introduce convex neural networks in the costs in the MPC scheme. Convex to make the optimization easier, and some other technical reasons. And neural networks because we also want rich functions in the learning. A few remarks and open issues. Again, I put the question mark for a reason in my title. I'm not saying that this whole thing is the holy grail, but it can help in a number of contexts, in my opinion. And one first remark is the question of economic versus tracking problems. I very briefly hinted at that in the beginning. So MPC is used a lot for tracking problems. So you try to bring the system to a reference, and you use a special cost function for that. That is conducive of bringing your system to that reference. When we do economic problems, we talk about economic MPC. The system performance is directly embedded in the cost function, and you're not trying to bring the system to a specific state. You just try to brute force maximize the performance of your system. When you talk about performance, in our experience, the learning plus MPC tools are more interesting for economic problems. If you really care about performance, if you care about tracking, you do learning over the MPC. Yes, you will gain some performance, but it's nothing spectacular. And I think the reason is coming from the roots of control, stability margins and this kind of things. You don't need a very good model to bring your system to a set points, but you need a good one if you want to optimize its performance. And safety, I discussed that. In my view, these RLMPC tools, they are not actually very good for the specific problem of managing safety. So in the safety slide, if you think about it, I was discussing the management of safety outside the learning, implicitly in the MPC scheme, not through the learning itself. So if you want to do safety through learning, you're probably better off going back to this machine learning over MPC model kind of approach. Try to capture via whichever ML tool you prefer the dispersion of your dynamics, and then treat that in the MPC scheme. So for safety, RL plus MPC is not your tool. It's your tool if you want to optimize the performance within that safety restrictions. Yeah, so from my experience, it's this RLMPC stuff is a good tool for designing MPC for performance on economic problems. And some open issues that we are trying to battle with is the obvious one now. So reinforcement learning, you typically need to crunch a lot of data. And of course, if you do RLMPC, you may have to do that as well. And when you do RL based on deep neural networks, crunching data means evaluating your deep neural network and maybe calculating the sensitivities. But when you do deep neural network, you typically have GPUs and graphic cards and so on that help you do that very efficiently. We don't have that for MPC. No one has designed this kind of tools for MPC. So that's then a lot of MPC solves, the equivalent of DNN evaluation. And that's a bottleneck when you treat a lot of data. So we are trying some new approaches for learning to reduce that issue, but that's clearly a bottleneck in the process. All right. If you want to hang with me for a few more minutes, I can talk a bit about an application, and I will detach a little bit from this theory and talk a bit more freely about something connected to that, but a little bit on a sidetrack. So is it okay, Rin? I still have a few minutes, or?
Yeah, I think people would be interested to hear a little bit about it. So. Very
good. Okay. So smart houses, that's one type of research I'm trying to push at my department. And just a bit of background on this, and that's about Norway. So Norway is the second highest consumer of electricity in the world, per capita, of course. It's actually twice the US. The first one, if you're curious, is Iceland. And it's not that we're a maniac with electricity, it's just that the society is built around electricity. We have a lot of hydropower and we're using it. And there are some regulations that make it this way. Heating is based on fuel is prohibited, so no gas, no fuel, nothing for heating, is purely electric. We have over 50% of the car sales is EVs at the moment. Smart meters are compulsory. And generally speaking, we have very strongly connected homes and appliances. it's very unusual today to have appliances that are not connected to the Wi-Fi. As a private consumer, you can really access the spot markets, just pay the price of the electricity, and there are very large fluctuation in these pricings. And there's a growing market for photovoltaic power and battery storage at home, typically using second life of EV batteries, because there is a lot of electric cars with soon to be retired batteries around. And there are experiments with smart grids, smart buildings, smart houses in Norway and in Scandinavia. But one observation that most people make is that all these experiments are too much focused on the power grid. So how can the consumer service the power grid as opposed to servicing itself or himself? So we're trying to do something to understand these aspects, not from top down, but bottom up. So what happens if you try to do things in a real life context? So this is a smart house experiment that we run at the department. It's a real house. It's actually this house with a northern light above it. It has air-to-air heat pumps, Mitsubishi ones, by the way, and a large ventilation system. All of that is connected through the Wi-Fi. The plan is to equip with more stuff like PVs, batteries, central heat pump, connected water heater, and so on and so forth. But here money is the bottleneck, so it will come over time. And we built an IoT system in that house, so for controlling the heat pumps, for measuring things. There are like 15 climate sensors, real-time power measurements, and all the data are logged all the time. So it's about 1 gigabyte of data per year that are collected on this system. So when you get all these things in place, you quickly realize what happens. So all these devices come with apps on your phone, and very quickly your phone is populated with dozens of these things. It's super nice, super fancy, but you also realize that there is close to zero value into this. It's just displaying data. If you want to actually do something, you need to bring the data together and start to do smart things with them. So that's the first aspect of the IoT: centralize the data, log them from all the sensors, all the devices. And that sounds easy, but there's actually quite some work in that process. You need to talk to the APIs. There are async IO aspects to manage, like real-time data streaming. You have a lot of glitches all the time in the system, a lot of data losses, reconnections, and so on and so forth. So the IoT, everyone talks about it, but it's far from being easy yet. So in the system, we collect all these data on a small computer, Raspberry Pi, using a Docker container system. So it's able to manage a number of tasks at the same time. It also provides an easy access, so you can very easily pull all the data you want from a side computer, for example, my laptop, at all time. And yeah, the system must be self-recovering. You have a lot of things happening and errors and problems when you manage the data. It has to survive all of this. But yeah, then you have a lot of data. That's just a representation of them in frequency plots. But when I wanted to give some things we learned by this experiment. So one lesson we learned on the IoT is that the value of the data is in centralizing them. That's obvious. IoT is still complex, even though we talk so much about it. It's still unreliable, and some providers are purposefully unhelpful. So they're trying to protect their business and prevent people from doing too good things with their tools. The second thing you want to do when you do these things is modeling the system. If you want to use this system to start managing the energy in your house, then you need to understand how that works. And here as well, there are some lessons learned. So of course you do data-based modeling of the house dynamics. We tried classic SysID more than we should have. It just doesn't work because the system is way too stochastic. We're trying some machine learning now. So one of my students is developing a temporal fusion transformer. And what we observe is that what can work is to use structured models with distributed parameters. So the parameters are not fixed. They are actually distributed according to some densities. And we'll do some hybrid AI next, so blending machine learning and structured modeling. Some lessons we discovered or learned the hard way is that house dynamics are simple but complex. They are simple in terms of qualitatively, right? If you raise the thermostat, temperature increases, power increases. But if you want to quantify how that's going to happen, that's where the pain starts. It's very stochastic, lots of unmeasured states or hidden states, if you want, which make it make the problem complex. So what we learn is that you should focus on simplicity and reliability in the modeling and on the parameter estimation. So we try to go for convex methods so that there is no problem of initialization and whatnot. We want actually methods that work reasonably well with limited data, because if you need to wait 1 year of data for having some kind of model working, well, that's 1 year where you've done nothing useful with the data. So you want models that are somewhat correct very quickly, which means you need to build a lot of prior knowledge into them. And what we discovered is that the model should capture the uncertainty. You should go for stochastic modeling and explain how wrong things can get. Then once you have some models, you go for optimal control. So the goal here is to beat the spot market. You can save quite a bit here by doing that, and that's an MHE MPC scheme running on the house. It's an economic objective, so it's trading comfort versus economics. And actually, here that's an example of what happens. You have power consumption on the right. The dark blue one is the hourly consumption, and the red stuff is a spot market swing. So it's going from around 60. The unit is øre per kilowatt hour. That's Norwegian stuff. But it's going from 60 to 225 at some point during the day, and then down, and then up again, and then down again, and so on. And the MPC scheme is seeing this swing coming and preheating the house. You see here the house raising in the different rooms, and then through this very expensive period, it's trying to survive on the heat stored in the house, in the rooms. And then it's negotiating the spot markets and the comfort settings of the users. And when you have these swings in the spot market, it's trying to heat when it's cheaper and reduce the heating when it's less expensive. And it's trying to do that in the most optimal way it can, according to the models. So the lessons we've learned from running about 1 year of MPC on this system is it's very effective at riding the spot markets. But we also know that the predictions are not very good. That's both for the temperature and the power consumed in the system. So it's very tricky to model these things well. It's also not easy to quantify the benefits because it's not repeatable. The spot market is not the same every day. The outdoor temperature is not the same every day. The stochasticity is not the same every day. And an important aspect is that the policy is difficult to explain to non-experts. Try to explain your grandma this system. So we need to have ways of showing people what's happening here and that it makes sense for them. So on this system, the plan will be to develop hybrid AI methods. That's, I think, the best for these problems. Why is it the best in my opinion? We have economic objectives. So it's resounding like MDPs and reinforcement learning. That's in a stochastic environment. We have this simple but complex dynamics. So here you want to blend knowledge-based and data-based in a really clever way. We have a lot of predictive information, the spot market, the weather, the demand, all these things. You have some predictions for that. That's a high dimensional information space that MPC can digest very efficiently. So MPC is a good tool in that context, but the models are not very good. So in my view, blending RLMPC will be a very good shot on this kind of systems. And the dream will be to democratize smart houses. So it should be simple, low cost, otherwise people will not use it. It should be adaptive and modular because houses are not the same. And it should be explainable and understandable, otherwise people will not know what's happening and will not want to use it. All try to fight the system. All right, that was my talk. I did not take too much time over the limits. If you are curious about the stuff I presented today, we have a lot of papers on the topic. That's just some of them. Yeah, if you have the slides, you can check that.
Great. Thank you very much for a very interesting talk.
Thanks for your attention.